welcome to numerical ship and offshore hydrodynamics. Today we have the lecture 28 and this is the lecture continuation of the discussion of the strip theory. Okay. And these are the keyword that you have to press to get this lecture. Okay. So, now let us start. Now, let us try to find out in the modern seakeeping and the ship motion computations that what are the available popular methods. Now, as you know that that one is we are discussing, like this is the strip theory. Okay. And then of course, we have to here you can see that there are many variants of the strip theories available, and how these variants and what are the variants. I mean, we can't discuss everything in a single course, but what we do is we are picking up one of the most popular one. Okay. So, we are going to pick one of the most popular one from this strip theories, but remember that there are many variants are available in industry. In fact, you know, something has the slender body theories. So, there are also many variants are available. Now, what is slender body? Definitely again we are going to discuss later on, but we really do not discuss much on this part. And in case of a three dimensional body, now these are whereas we can call popularly call as two dimensional theories, because here mostly we are finding out the disturbance at each strips, and you can assume that each strip is a two dimensional body. So, that is why you can say, but at the end definitely we are going to get a effect for a three dimensional realistic surface. Okay. It is not like that using strip theory you are getting a it is that added mass damping for a strip. Of course, that is the primarily we do that, but at the end we can combine all this two dimensional effect and we can get the three dimensional effect out of it. So, strictly speaking, telling two dimension theory may not be fully correct, but in a sense that we are interested to get the two dimensional property at a two dimensional strip, and then from that property we try to find out that what is the overall effect for the three dimensional body. However, in three dimensional theories, this one from the beginning we are taking a three dimensional body. So, there we do not have to do any simplifications by cutting the ship in different sections, that we do not do for the 3D theories. And you know that for the panel method what we did is we get a geometry and then we get a panel, right. All the panels are three dimensional panel or two dimensional, I mean that three dimensional surface, inclined surface, and then we try to find out that what the quantity, the pressure at each panel, so we integrate, get the force over the body. So, that is what we call a three dimensional theories, right. Now, if I consider the three dimensional theory, then again here having a frequency domain solution, we can call the Green's function based method, like the frequency domain Green's function for the forward speed, and also we can have the Rankine panel. Now, Rankine panel method, as I discussed before also, here this also could be in frequency domain, could be in time domain also. Okay. And then but why the difference is because this Rankine, the Green's function is nothing but 1 upon r, it is does not depend on the frequency or time. So, it can be applied here both. Now, in case of a Green's function based method, we are using, of course, we are using this 1 upon r, but apart from that we have some kind of a function we can call the harmonic oscillation, right, which is the depending on the position p and then position q. Now, by this time you should know what is position p, what is position q, and it is depending on the omega, or we can call is a pulsative Green's function. And now, we have not discussed yet that this the last variant, which is time domain Green's function method. Definitely we are going to discuss in future, but the primary difference is everything is same. This part is same for every panel method, but apart from that we can have some impulsive Green's function, which is function of p, q, t and tau. I mean, what is all this these things we are going to discuss later on, but okay. So, but now here let us focus on the strip theory. Okay. Now, most widely used method, of course, like apart from all this method, the panel method, the Rankine based panel method, which is 1 upon r, or frequency domain panel method, you take everything, most widely used is the strip theory. Now, people will, I mean, maybe a little bit skeptical, like why we can say that, why it is not skeptical. So, I will say that maybe wondering why the strip theory is most popular, because we know that if there is some sophisticated method, people would like to use the sophisticated method. Now, if you look at the sophistication, definitely the 3-dimensional panel methods are much more sophisticated compared to the 2-dimensional strip theory, but still why it is so popular. Now, surprisingly, what we have seen that now if you considering that if you are considering that we are only looking for the global motion, for example, I am looking for the RAOs only. Okay. Sorry. So, now if I look for the global motion, for example, I am only interested in RAO. So, it is nothing but the frequency versus amplitude, right. Let us take xi 3 by A3. Now, if my focus is this, then strip theory is very good when we actually look for these global parameters like the RAOs and then the global force, etc., etc. Now, sometimes actually we really try to understand some local pressure zone also, local pressure field also. Now, suppose I have a shape, let us try to get some 3-dimensional field. We have a shape like this, let us say, and maybe we are trying to figure out that pressure variation along the depth, the pressure variation along the depth, maybe it is Z, and then you can say the pressure variation along the X also. Now, if you do some kind of this detailed analysis, that time strip theory is not good. Okay. But most of the time we are normally we try to find out what is the response, the global response, not the local response. Now, once you do that, that time definitely strip theory is of course most preferred theory compared to the 3-dimensional sophisticated panel methods. Okay. Now, what does strip theory means? We have not yet discussed what strip theory means. Okay. Definitely we are going to discuss today. Now, are all strip theories same? As I said, no, or if they differ, then where is, I mean that what would be the consequence for the prediction? Like if I say that this is the strip theory 1, it is, and then you have strip theory 2, and you have the strip theory 3, 3 types of strip theory, and you are trying to figure out the global motion using this strip theory. Let us say that the ship is same, so geometry of the vessel is same, and then also the frequency also same, let us say, or the frequency range is also same. Now there should be unique answer, right. Now, if I say that I am using the different level of numerical methods, then what is the implication or what is the consequence in the final answer? That also that is something that we need to really bother, right, because definitely results might differ, but at which extent? So, therefore, what we need to understand that what is the limitations of the strip theory and where people are making assumptions, and then what would be the consequence of these assumptions on the global when you get the global motion, compute the global motion, right. So, that is what actually we need to understand more, like that is what this course all about, to discuss that the limitations and their consequence in the final results. Now, what are the details embedded in a component of the strip theory. So, let us discuss then what is the details of computations that embedded in the strip theory. Okay. So, let us now here it is. So, let us see that what actually we are doing when you solve the strip theory. Now, this hull is divided into the finite number of 2D strips. So, this is the first thing, that is why I call this a two dimensional method, because if I have a ship, suppose I have a ship something like this. So, what I do is I make some finite number of strips, we cut the ship in this finite number. Now, if I take out any of this, then definitely we can have some kind of different kind of shape, right. So, now this is your two dimensional body, right. So, that is why I said, that is why normally people say that is a two dimensional theory, right. However, one must remember, I said this so many times, the final results we are trying to figure out that the pressure over the three dimensional body only, right. Okay. Then hull they divide into finite number of two dimensional strip along its length, and then the three dimensional hydrodynamic problem is reduced to set of two dimensional hydrodynamic problem. So, that means now I am solving this two dimensional problem of this is my body, and I try to figure out that all this component like which is necessary to get the equation of motion, that means that added mass. So, we can call this added mass 2D, we can call the damping 2D, right. We can call the exciting force or F, or we can call that the FD, okay, that is also a two dimensional component. So, we try to figure out all this two dimensional component for each strip. So, therefore, this three dimensional. So, finally, my aim is to get the three dimensional added mass, right, okay, or maybe the three dimensional damping, and also maybe the three dimensional exciting force. However, I am having all these parameter for each strip. So, then how can we combine everything to get the three dimensional fill, right. So, we do the opposite, this 3D body I split into set of strips, and each strip I am try to find out the hydrodynamic parameters. So, that is the same thing written over here, the hydrodynamic coefficient associated with each strip are given by the solution of the two dimensional boundary value problem. So, this is also very important thing, right. We are finding out a two dimensional boundary value problem. Now, whatever discussed here till today, when you do the frequency domain solution, we have discussed the three dimensional boundary value problem all the time, right. But here we are going to discuss what is the two dimensional boundary value problem, right. Okay. It is assumed that flow around each strip does not affect the flow on the adjacent strip. So, this is a very important approximation, because here otherwise we have lot of problems if we do not do this approximation. Now, people have come up with somebody called the 2.5D method, where they do consider this, but in strip theory what what we are trying to say is as follows. Suppose I have a ship and let us cut into number of pieces this way. Now, when I solve, let us say section 1, this is section 2, this is 3, this is 4, this is 5, let us say this is 6. Now, I say when I solve the boundary value problem, we can call the BVP boundary value problem for strip 1. So, then you have the flow in all direction, right. I mean, therefore, the effect. So, now what happened, like when I solve the, let us say, radiation problem. So, it means that this strip, if I let us say this is the strip. Now, what is happening radiation problem is that I am oscillating in this, let us say, some heave mode. Okay. Now, when I oscillate this in the heave mode, then definitely I get some waves in all the side. So, therefore, we are going to solve for the second strip, there should be some effect of the wave that coming from the first strip. Normally, there should have some effect, right. So, that means what I am trying to say as follows, when I am solving the boundary value problem BVP for the second strip, there must be some effect that comes from the first strip, that so we assume that there is no effect. So, we treat the each boundary value problem, each strip, this two dimensional boundary value problem is independent of the effect of the adjacent strip. Okay. And therefore, this is a huge assumption, right, because we are assuming that the flow it does not propagate in the longitudinal direction, right, that effect. And then so because of that there must be some kind of maybe some effect, we do not know. Okay. That is why later on people have come up with some, we call it the 2.5D method. So, it is not 2D method, 2.5D method. That time they are doing again the strip, but again they considering some effect when you calculate the adjacent strip when try to figure out this radial damping, they do consider the effect from the adjacent strips. But we are not going to discuss this. Okay. We only we focus only on the strip theory. Now, last point say that the 3-dimensional hydrodynamic effect are related to the forward speed only, right, and the result is coming because of the angle of attack. Okay. So, it means that here this forward speed effect is that 3-dimensional effect are associated with the forward speed and then the angle of attack. So, normally all the time you do not consider, you are not encountering the head wave, right. Sometimes that waves may be coming from the beam C location 90 degrees, sometimes from here, sometimes from here, right. So, therefore, this 3-dimensional effect is related to this one. Okay. Okay. So, now this is the overall picture now it is little bit clear to everybody. So, that is how we just in this picture we have cut this so this strip in this YZ plane, right, and then this is the corresponding the diagram. Now, you see here when you oscillate this, so we assume that this wave is created in this transverse direction, right. So, there is no flow in this the longitudinal direction, right, fine. So, this is how actually graphically you can represent what I said, right. Now, this as I said that 2-dimensional flow in the strip, there is no there is no flow around this longitudinal body. So, it means that when you oscillate this two dimensional strip over here, this flow does not affect the this direction, right. It can only go this way, right. And then now you can consider these as a two dimensional effect here. Now, if you integrate along here to here, we can say we can get the three dimensional effects, right. So, now till this point people might think that this two dimensional effect, I mean this three dimensional effect is coming only by integrating the two dimensional effect, right. That might be the general notion, right. But now let us see now let us see that actually the assumptions, and then as I said that we have some feeling that only integration of the two dimensional strip over the length gives you the three dimensional effect, right, and that is the all about for the strip theory. Now, let us see what is written over here. Now, here again is just a summary type. Now, all the strip methods or strip theory methods does assume that thin long strip, right, that B by L ratio assume to be small. That means that length is much larger, I mean if you compare to the B. So, we can assume that it is the thin strip. That means, if you look at the from the top, then we can assume that the strip is like this. It is not like this. Okay, so this is called the slender body. Okay, fine. And then the two dimensional sectional hydrodynamic property, I mean we are getting by, and if we integrate it, we are getting the three dimensional quantity. Now, look at the third point. It says that this 2D sectional hydrodynamic for the 0 speed. Now, my question is this: if we assume the strip theory means that integration of the two dimensional property along the length, but then how it works for the forward speed? Because all this two dimensional property actually we are doing it for the 0 speed. Now, how can this apply for the forward speed? Now, you see, if you think of the the strip theory mean like that very simplified statement is, I am having the two dimensional strips, I integrate it, I get the three dimensional overall the property. No, it is not like that, because this two dimensional property, the radiant mass, that damping, that two dimensional radiant mass, two dimensional damping, all we are getting for the 0 speed. So, the strip theory means how actually we can incorporate this forward speed effect. So, that is the next point. Then what does this forward speed dependence taken care of, and that is the essence of the strip theory. Okay. So, that means again that how we are accounting the forward speed, that is also not unique. It is not that there is only one method. So, there are many theoretical development is there. So, because of many theoretical development, then many theory exists for that, and also sometimes that we need to give a special treatment for the different type of ship, which something has that cruiser stern, something has the transom stern. So, based on that also we can have some truncated conditions also one need to put. So, it is the huge huge development, huge thinking on each methods, right. So, then where these various versions of the strip theory differ. Now, you see that First is accounting of the forward speed, how I can taken care of the forward speed. So, there is a different theory available for that. Now, if you account in different way, then your mathematical derivation of also different, right. So these are the difference, that's how the different strip theory that different strip theory exists, because of I do not say limitation, I said that by this incorporation of the forward speed. Okay. Now, because you have make an approximation that all theory have some approximation. So, therefore, most popular approximations are it is a, we can call it a high frequency and low speed phenomena. So you know, we can say that this strip theories mostly we can account for the high frequency and also is a low speed phenomena. This allow to make a simplified solution for this problem. Otherwise, you know, because you see, if is a if you do not consider these things, then how we account for the disturbance created by shift for the longitudinal directions, right? And then how we can you know, deals with the radiated wave. Now, you see, now if you remember that we are throwing a stone in a pond, then we have seen that this radiated wave field is going in a circular fashion, right, in this way. But however, in two dimensional case we cannot see this phenomenon. We assume that all this wave propagated in this manner, in two dimensional manner, right. So, how we can account for all these things, right. And also, as I said that in exciting force also there are lot of assumptions, people are making lot of simplification to compute the exciting force. So, that also affect the final results. Okay. So, now in this class normally we focus on two major assumptions. One is the beam is much smaller compared to the length. Okay. Therefore, the longitudinal component of the unit vector normal to the hull surface, and that may be neglected. So, this is number one, and then the frequency of oscillation is high. Therefore, the free surface boundary condition may be assumed 2D. Okay. Now, you know, that is how, like as I said, in other words, if I do not assume this, in high frequency still it is valid that all this propagation is parallel to each other. However, most of the time, if you, as I said, that if I put a stone in the pond, then we see that wave is propagating in this fashion. So, this wave is propagating in all direction, it does not propagate in one direction, right. So, therefore, but as I said, if I assume this frequency of encounter is very high, in that region one can assume that this forward speed, I mean this effect, the radiated waves are not propagating in the 3-dimensional way, they can propagate in a 2-dimensional fashion. Okay. So, you know, this is why we are assuming all these things, right, because we try to find out some way so that this 2-dimensional theory can be applicable. Now, we can understand, at least we can understand at this point, it is not applicable everywhere, right. The radiation field, it is 3-dimensional field. So, only in high frequency zone it could be approximated as a 2-dimensional field. Also, this longitudinal direction we really do not consider any effect, that, right. So, therefore, the ship has to be slender. So, therefore, this strip theory is not popular for the offshore industry, because we are dealing with some offshore structure where this L by B ratio is more or less 1. So, that time you really do not you really can't use this sort of approximation. Okay. So, today we stop here, and then from the next class we are going to discuss the mathematical equations. We started the 3 dimensional equation, and under these assumptions how we can write the 2 dimensional equation. All these things we are going to discuss in the next class. Okay? Thank you.